So, we will discuss in this lecture about martensites. By the way, martensite is named after scientist Martens. He discovered this thing first time, and that is why we call it martensites. As I told you that martensite forms when you quench austenite from high temperature. So, quenching can be done in water, or you can do it in liquid nitrogen, or one can do it in ice. Depending on the quenching, the martensite volume fraction will be changed in the microstructure. First, let us look at how it looks like, then we will discuss about details. Remember, martensite itself is a subject and it cannot be discussed in one lecture or two lectures. Whatever the basic features of martensite of steel I am going to discuss. To be clear, martensite is also observed in non-ferrous alloys. So, it is a common feature in many of the microstructure. So, martensite is true in general. On the other hand, perlite and the bainite is very specific to the steel. So, martensite is observed in nickel based superalloys, even some copper alloys. We use martensite transformation is nickel titanium alloys for the shape memory effects. So, therefore, martensite is not only present in steels. But in this discussion, we are discussing about martensites in steels. Martensite looks like a plate or a lath in the microstructure. As you see here, this is a typical microstructure of a martensites. These things, grey color plates, they are actually martensites. In between white things which you see here, that is basically known as written austenite, written gamma, and these are actually martensite. Many books they represent as a alpha prime. To distinguish between alpha, martensite as a distinct crystal structure is known as polycenter tetragonal. Basically, very low carbon concentration steel, the martensite tetragonality is very low. Remember, we define tetragonal crystal structure by two lattice parameter A and C. In cubic, we have a lattice parameter A, because in cube all the sides are of similar length and angle between each side is 90 degree. In tetragonal structure, the two sides have the same length, but one side has a higher length, that is in a tetragon, and angles between all the sides are 90 degree. So, tetragonality is defined by ratio C by A. C by A is basically a function of carbon concentration in the steel for martensites. So, when carbon concentration is very low, the C by A ratio is very small. Sometimes we cannot distinguish between cubic or tetragonal structure or low carbon concentration steel in martensites. So, therefore, we represent this as alpha prime, because it is a derivative structure of alpha. Now, martensites, as you see here, this is an optical microstructure, looks like a plates, and if you look at a much large, much lower magnification microstructure, what you see here? You see here, these are actually alpha gamma grains, okay, and martensite forms like a plates. You see that everywhere. In fact, they looks like this, okay, or looks like, some cases looks like such a kind of structure. I am drawing one of them, okay, in some cases they looks like this. They are actually internally twinned. They have twinned inside each of these martensites. That is why they looks like a faulted. So, therefore, martensites basically forms what is known as a diffusionless transformation, in which none of these species, either carbon or iron or whatever present in the steel, undergoes any diffusion. They goes as suppling basically by shear force, okay, because it is quenched to water or some other things. There is no time for any diffusion of the atoms to happen, because diffusion requires time, as you know, okay. So, therefore, we cannot actually have any choice other than transformation which is dictated by application of shear forces. So, just to give an example, just martensite is basically like this. Suppose you have in a classroom, you have chairs are kept in a particular manner, okay, and if you ask the students to be just like behave like atom, they can go and sit and in a particular order, suppose in a gamma iron. Now, once you cool down to lower temperature very slowly, these atoms can then change their positions, and basically that is nothing but these students can change their positions and segregate. So when they segregate, they form perlite. That is why carbon diffuses out from the alpha and go to cementite. But if we don't give them time, suppose if the students has to enter the class and sit very fast, so they will simply occupy the positions wherever it's available. So that is nothing but, actually saying the atoms in a material to simply go to a seated positions and don't move. Exactly that is what happens in the martensite transformations. The carbon atoms are actually pushed, okay, along the C axis of these, along the one of the axes of these cubic unit cells, and that's why actually they become align along certain directions and tetragonality develops. That is one of the important features of martensites, that they say diffusion-led transformations. As I said, the plates, if you look at very carefully, plates are actually internal twins. You can see these are all twin presents inside that. Every plate martensite has a twin structure. That is obvious because you are actually forming from a high temperature by quenching, and this has to adjust its orientation with respect to the prior gamma grains. So to do that, it creates a lot of defects inside, and easiest defects to form is basically twin, because that can take care of a lot of strain, because higher the number of twins, higher amount of strain can be accommodated. So that means what? Martensite transformation involves a lot of strain, plastic strain basically, and this plastic strain can only be accommodated by either by dislocation motion or twins, but twins are better because twins can accommodate more strain as compared to the dislocation. That is why all these martensites in the steel has internally twin structures, which is very normal in these martensite structure. Because these are distorted and this has internally twin structure, therefore they are very hard. They are extremely hard actually. Martensite in the steel has the highest hardness. If you look at Rockwell scale, martensite is a hardness above 60 in C scale. 60 to 65 is the hardness of martensite depending on the carbon concentrations. On the other hand, perlite and benite has a hardness less than 50. So therefore there is a huge difference of hardnesses of martensite and the other phases in the other species in the steel. This is the reason actually why they have this kind of structures. So to give you a better idea, you can see here the twins. You can see this is a twinning plane and these are the twins. Very nicely you can see the twins. So twinning is easily observed, internal twinning in the martensitic planes, and this is the reason actually why martensites are hard. Again I am showing you here a plot. This may not look so good between hardness and the carbon concentration. This is the hardness of the benites. It increases as a function of carbon, but not more than 300 in a Vickers hardness level. Martensite hardness, you can see it is very high. It increases function of carbon, it can reach up to 900 actually. And so therefore it is about 0.6 is what is the weight percent of carbon at which the martensite hardness is maximum. After that martensite hardness decreases, that mainly because amount of written austenite increases. So first of all, why do you have written austenite in the microstructure? Let us also discuss that part, because that is very important, because that dictates the total hardness of these martensites. Remember, martensite actually forming from high temperature by quenching, therefore they form by a shear deformation process. And when they form, because undercooling is very large, you are quenching gamma phase from 950 to room temperature. So quenching is the undercooling is of the order of 7 to 800 or even sometimes higher than that degrees Celsius Kelvin. Such a large amount of undercooling, what will happen? Because it is a large amount of undercooling, so driving force per transformation is very large, and because it has been quenched into such a fast way and diffusion cannot happen, so diffusion is also not possible. So therefore martensite plates started forming in a peculiar manner, or actually it happens in a burst, just like this picture I showed you. It happens like a burst. You see here, these are the grains of the gamma. So martensite plates have formed like a burst. Large number of martensite plates nucleate and grow very fast. So it is very difficult to distinguish between growth and nucleation and growth, but they actually form like a burst. And because they form and they are twin, they are having a lot of defect structure, this free energy which is available for is large undercooling is taken away by these deformed structure by internal stewing structure. All the free energy will be taken away. Remember, this strain energy is basically a positive term in the free energy expression. So total free energy has a volume free energy plus strain energy plus the surface energy, right. So because of this the free energy which is volume free energy which is available to the system to do the work, bulk of it is taken away by the strain energy. So therefore, when it started transforming a large number of martensite forms in the microstructure, if all the free energy available, chemical free energy available to the system is eaten away by the surface energy as well as the strain energy, there will be no free energy available for further transformation, and that is why actually you have some austenite retained in the microstructure. So it is never possible to produce 100% martensites. You can always get about 90 to 95% martensite in the microstructure. Some amount of written austenite will retain, but remember the written austenite is very bad as far as mechanical property is concerned. Why? Because the interface between martensite and written austenite is very strained, and the cracks normally originate when you apply force on these steels from these pieces, and then it can lead to catastrophic failures. That is one of the biggest problem in the martensitic steels. Okay, so that is one part, and this is what is shown there. You can see here martensites, internal twin structure, martensite plates. Okay, internal twin structure, martensite plates are seen. Now, the reason actually it has a different hardness as a function of carbon concentration is because the carbon is a species which actually gets suppled from one position to the other position, from FCC position to the edge corners in the BCC, in the BCD structure, and because it is basically going in that way, that means they are actually getting suppled, and that is why actually the amount depending on the carbon concentration presents, there is an optimum value of the hardness. When it increases, suppling is no longer can be done effectively, so therefore strain build up is also low, hardness drops. Secondly, as the carbon concentration increases, the driving force available is also eaten away mostly by the strain. Written austenite concentration is more, or volume fraction is more in the microstructure. The strain energy is sufficient enough to allow written austenite to be present in the microstructure in large volume fraction, and written austenite is very in a soft phase, so therefore hardness drops off. As I said, the martensite is actually not doesn't actually lead to good mechanical properties as far as the combination of strength and ductility and toughness is concerned. Martensite is hard, so therefore it can give you very high strength, but its ductility is poor. So therefore always martensite is tempered, or martensite is basically kind of transformed by aging at different temperatures, and this is done in different ways. Remember, martensites can be tempered at different temperatures. Depending on the temperature of the tempering, martensites can have different product. So as you know, very low temperature annealing treatments at about 100 degrees Celsius temperature can lead to reorganization of these defect structure in the martensitic plates. And what is the meaning of that? The meaning of these, the dislocation of twins will arrange nicely in the microstructure. As you see here, twins are the arranging like this, and these are the dislocations present in the microstructure, and they actually arrange in such a way that their energy gets reduced. That is what is known as a reorganization of the defect structures. That happens at lower temperature. But this will not reduce this will not lead to improvement of the ductility. This will lead to relaxation of the stress, because there are a lot of stresses inside it because of this defect structure. This can be reduced a little bit by reorganizing them properly. Now second is this, if you heat little higher from 100 to 250 Celsius temperature, it can lead to new phases formation, and these new phases can be epsilon carbides, what is known as Fe 2.4C. Okay, that is what happens in some of these the temperatures. This epsilon carbide precipitates, basically what has happened, martensite is basically a supersaturated solution of carbon in iron having a BCT structure. Okay. So therefore this excess carbon which is present has to come out somehow to basically maintain the equilibrium or metastable equilibrium in the system. So one of the ways to do that is to form a carbide which is non-stoichiometric like Fe 4.2C. This is known as epsilon carbide in the literature compared to Fe3C. So these carbides will always forms on the defect structures. That is what you see here. In these dislocations can be actually, or twins can be nucleation points for these carbides. So these carbides will similarly nucleate along these defects and grow. That is the way carbon can be taken away. Now if you hit middle further from 250 to 350 Celsius temperature, some other carbides forms like Fe2.6C, even some carbides can be formed, and these carbides looks like a different morphology in the microstructure. So by simply precipitating different carbides, the carbon concentrations which are present, supersaturated carbon present in these grains can be taken care of. Okay, that is what happens. So slowly the grains of martensites will become lean in carbon. Now as you heat very high temperatures, something like very close to these eutectoid transformation temperature, something like about 650 to 700 Celsius temperature, these carbides will start becoming Fe3C, or basically they will become cementite. And not only that, cementite carbides will looks like a spherical, because at a high temperature they can actually form nice distorted sphere structures, and they can form along the boundaries or inside these defect structures also, which are present still in the microstructure. And because Fe3C will come out, remaining grains will become alpha. So complete carbon partitioning happens from the grains of martensite to Fe3C, and slowly Fe2.4C, Fe2.46C will transform to Fe3C. So finally we will have a microstructure with a coarse Fe3C near spherical structure along with the alpha grains, same like a perlite or benite, same kind of phases. So as you see, our final phases almost remain same, whether it is you start with a gamma to perlite, gamma to benite, or gamma to the martensites and then heat treat it. It does not matter whichever paths we take, phase mixture will become similar at the end, but morphologically they are distinctly different. So therefore, depending on our requirements in the actual mechanical physical properties, this heat treatment temperature and time can be controlled for the martensites. Martensite can be tempered at different temperature, different time scale based on the requirements from the user, the strength level, ductility level, toughness level, as well as any other physical properties which are required by the customer. So this is a typical heat treatment cycle normally is done. So let us now discuss a bit about nucleation of martensite. As I said to you that nucleation is very important in martensite transformations. So we will again do the two-dimensional one. Let us assume that this is a undistorted austenitic cell, so therefore there is no distortions, and as you know the martensites actually looks like a lens-shaped elliptical structure. Okay, we can actually do the twinning like this way to show that. So that means what? The distortion of these to these is accompanied by a twin, and this means that the twinning leads to a lot of defects inside the martensites. So if this has to be a crystallographically important feature, so that means the nucleation process must take care the distortion process, these sort of things. So as you know, the total free energy system, if a difference basically can be because of the we can write down like this. This is V GV, that's the chemical free energy part, plus A gamma. A is the area and gamma is the interfacial energy. That's all is present in a nucleation process. We have seen that, right? Because this is the available energy to the system, that's volumetric term, this is the area term. Now because of the distortion we need to add one more term, and that's the strain energy term. That's also basically related to volume. So I can write down volume multiplied by the strain energy. That's strain energy reflects in terms of delta GVS. So now if I assume that this ellipse has a major axis of 2c, this is the length, so that means C is the major axis and A is the minor axis. As you know, A is the minor axis, so this is 2A and this length is 2C. So if I assume that, then we can actually get these values, volume and the area, very easily. That is what I have done. So I will write down that A is basically equal to twice pi A square. Okay, that is possible to calculate area of the ellipse, and volume will be equal to, volume is basically equal to 4/3 pi A square C. That is also understandable, but the difference will come in the strain energy term. So let us write down that delta G is basically nothing but minus 4/3 pi A square C delta GV plus 2 pi A square gamma. Gamma is the interfacial energy between austenite and martensites. Strain energy term, it has to be determined very nicely. This will be equal to 2 nu, nu is the shear modulus, okay. V is the okay, no, this is S by 2 whole square. I have to check now what is S, and 2 minus nu, 2 nu is the Poisson ratio, 1 minus nu, okay, there has to be 2 here, okay, and multiplied by pi C by A, and this again, this is the strain energy term actually total, multiplied by volume, correct. That is what is the thing. This S is basically shear strain, shear actually, particular shear. Okay, that is the reason, that is the main factor which leads to this kind of a this twinning. So now one can actually do every analysis. So this is my total free energy. So this V can be again written as 4/3 pi A square C. Okay. So you can actually take this expression and do d delta G by dA equal to 0 and dG, d delta G dC equal to 0. You have to understand there are two parameters here. It is not no longer a sphere, it is basically an ellipse. So therefore you have a, you have a C, and because you have two parameters, the minimization requires differentiation with respect to both of them to go to 0. So once you do that, then you will see that C star, which is nothing but a critical value of C, that will be equal to again same as A star, or same as R star actually we have seen, but A star will be a complex things, little bit different. A star is basically to 16 comma nu. Okay, we always assume nu, this nu is basically 1/3 in metal, always assume that is basically 1/3, remember that, you can replace that also. So that is actually A star equal to, no, that is not actually A star equal to mu gamma, this is S by 2 whole square divided by pi, no, pi is not there, delta GV square, yes, it's correct. And delta G star is a much more different, distinct thing, that is very important for us, 5/12 by 3 gamma q, obviously. Remember this is not 16 by 3, this is 5/12 by 3, okay, by delta GV to the power 4, not square, and S by 2 4 multiplied by mu square pi, and this is equal to joule per nucleus. So what is important for you? For you, important is to know this expression basically. This expression tells you, obviously this expression tells you delta G star is a strong function of gamma, but it is a much stronger function of delta GV and S, the shear strength, okay, and the shear modulus. This is what is important. So as you see here, these values, shear strain increases, delta G star height increases. So that is why nucleation is difficult, because every transformation from austenite to martensite requires shear strain, requires shear, and that is what makes this nucleation very difficult. And that is why actually nucleation in martensites takes a lot of energy. And this is one thing. Second important part is that this free energy, if you look at this, is total free energy both for nucleation and growth. And as growth is very fast, we have only considered this as a homogeneous nucleation here. We have not considered heterogeneous part. It can happen anywhere in the inside these grains, or there is no preferential things about the grain boundaries being a nucleation site for martensites. But if this is my free energy available to me chemically because of quenching, this is used to create interface to take care of strain. Now interface is fine, you are forming a new phase, interface will be there. But here the interface energy will not be very high. Why? Because there is a distinct crystallographic relationship between martensite and austenite. But important thing which will be high here is this part, the strain energy part, and this is substantially higher as compared to the surface energy parts. And because it is higher, this actually takes away lot of the chemical free energy available to the system, and that makes the transformations incomplete even if you quench liquid nitrogen temperature. And this is the reason austenite is retained in the microstructure. Austenite can never be fully transformed to martensites because of this strain energy. This energy takes away a lot of part of the chemical free energy, and that is also evident when you calculate nucleation barrier. So these are the things you must remember, because these are not taught in the normal lectures or normal textbooks. It is there in the book, and you should look at it in a detailed manner so that it helps you to understand the transformation better way.